You got the lecture notes for the second lecture?
Some of us. Ah, we want them, yeah.
I uploaded it the next day, the lecture, but then I forgot to save it. So I didn't know it. So somebody came to my office yesterday and he told me that it is not there, so I uploaded it again. If something of this kind of thing happens, just message me. Okay. It happens. Okay. So today we will finish our analysis of ideal flows. You are new.
Yes.
You also new.
Yeah.
Welcome. Okay. You also new.
I was the boss for the first two lectures.
Your name is?
Idan.
Idan. Okay. I remember you. Alright. And some of us disappeared. Okay. Some came from abroad, some went abroad.
I know a few people told me they're going to be watching on YouTube live.
Some told me as well. Anyway, so we are continuing our discussion about ideal flows, invisible flows without viscosity, no dissipation. And today we will complete our discussion. The first part of the course, which is invisible flows. Okay, so what we have studied so far, let's summarize this. We studied that in invisible flows, if you do not add any mass from outside, mass remains conserved. And that we represented by continuity equation. We also showed that in the same flows, momentum and energy is also conserved. So we have three conservation principles: mass, momentum, and energy. And then we studied the fluxes of momentum and energy correspondingly. But below this theorem. Okay.
Can we describe like fluxes in a system without it being conserved?
Flux?
Can we describe flux of like a vector quantity or scalar quantity like momentum or energy without it being conserved? Or is it like how you can only have potential for a vector if it's curly zero? Or
Question is not clear. Can we represent momentum and
because it felt like a really general like thing that we did. Like this is just a way to quantify a thing that goes from this place to that place. Can we do that for any sort of vector field without any restrictions?
any sort of?
Like scalar or vector quantity or thing?
Yes. So we saw that mass is scalar.
Yeah.
Momentum is tensor.
Yeah.
Momentum flux is a tensor. Momentum is a vector. And energy is
Yes.
scalar. The energy flux is vector.
Okay.
So is that the question?
Not really, but it's okay. Not
No. Try to clear it. Everything should be very clear. I did not understand.
I was just thinking about how like when you have a vector field like a dielectric field, that it doesn't have like a conservative force. You can have a potential for that field.
Right.
That potential is a much simpler way to describe the vector field that only works with some restrictions, which is it has to be non-rotational.
Right.
So is that the same for what we're doing here? Is the fact that we have the energy defined at every point or something like that?
No.
Okay.
No.
Okay.
But it's important. We will cover the circulation theorem today, where we show that if the rotation is zero in a fluid, the velocity can also be represented like a potential. We call it velocity potential. However, the argument is different.
Okay.
Any physical quantity which is flowing, if you do not add the quantity from outside, it remains conserved. It's a very trivial statement, but we saw that how important it is to formulate it mathematically. Okay. I repeat, if anything is not clear, stop and ask. Okay? Because if you pass through, then you will not understand what it is. Now we find a way to write all the conservation equations in the same form. Okay. As we discussed, let's summarize our previous equations.
4.
This is mass conservation. Let's call this P, P0 momentum. Smart divergence. This is momentum flux. Then we get energy flux. We wrote these in form of components, but then we represented the density, the mass, and the energy in form of simple diameters. Just way of representation. Why we showed the middle equation in the form of components? Because the momentum flux, the pi ik, is second order tensor. And that's just way of representation. Now we show that all these equations can be shown in single matrix form to understand their physical nature. This is the combined form of all the equations, where U represents the conserved quantity. So U is rho and Fu is the corresponding fluxes. This is pi I here. What is W here?
In the z part of the first vector, why is the epsilon multiplied by rho? When on the right side, when you wrote what u is the definition of u, the epsilon is not multiplied by rho. So
Well, which one? Here?
here you have epsilon times rho.
Right.
There, where you said the definition of u, you do not have epsilon times rho. You only have. Okay.
Understand. Yeah. What is W here? What is W here? Enthalpy. Alright. So this is the way to why I write it in matrix form. And here the I is unit matrix, and V cross V means the different components of V, all the components of multiplication. It's rho Vi Vk. This is how we wrote there in pi ik, and P is pressure, which is isotopic. I represents P only has diagonal terms. Okay, same. Where V and this V have same components, only then P matters. This is what we saw in last lecture. So the way we write it, it shows that all the conserved quantities, namely density, energy, and momentum, have same physical nature. They are conserved. When does this equation break?
When there are outside forces.
Huh?
When there are outside forces.
If the outside forces, there is external momentum flow in the system. But even in that case, momentum flux remains conserved. It breaks in specific. Okay. First of all, this whole setup is for ideal flows, where there is no dissipation. Okay. And we discussed that ideal flows actually do not exist. So it's for ideal flows, they do not dissipate their energy. Number one. Number two, the flow is isentropic. If we do not use isentropic flows, when we derive this energy conservation, it has entropy terms in between. We change the entropy. Okay. ds, dt maybe. So these conservation quantities or these equations are specifically applicable for ideal flows and isentropic flows. What are isentropic flows?
Reversible and
adiabatic. You don't have turbulence and stuff to speak.
Turbulence is okay. Isentropic is bigger than that. Even if the flow does not have turbulence, it may still not be isentropic.
when
So,
the
is it-
ds is zero, when the entropy.
Yes, but physically what that means.
You could theoretically reverse it. It's not like a bunch of fluid
No heat flow.
starting off chaotic and being.
Inside outside, and it's reversible. So with the
So
No heat exchange, and you can undo the process.
no heat exchange from the outside
Yeah,
the system, and
You can undo the. You can reverse the.
yes, it's reversible. Okay, these are two requirements. Once you have all these assumptions, the equations are strictly valid. Okay. And remove them. Okay. Incompressible fluids. What are incompressible fluids?
Rho is constant.
Like
water.
water and air.
You can compress there a lot.
Air is compressible.
Very
Water
good.
is water ideally compressible? Incompressible.
Yeah.
Water is not no fluid is ideally incompressible. But if we apply a lot of force on water, its volume changes negligible. 0.001% something. Once you double the pressure from the atmospheric pressure. Okay. So again, so we can consider it to be an incompressible fluid. In continuity equation, we showed that incompressible fluids have zero divergence of velocity. Remember that? How did we show it? And what it means?
Density does not change.
Density does not change, fine, but now we have velocity here. If density doesn't change, velocity cannot diverge.
Yeah. If you have like a region and then you run the region forward, it can't become, the area it represents can become larger or smaller.
Which region?
A volume of a liter of water, if you look at every molecule in a liter of water and you run this simulation and you like run the clock forward and you look at the shape of it now, it's still a liter. It can't be less, it can't. It's the divergence.
The volume is constant.
Volume is constant.
Volume is constant. It cannot diverge. No? If you take a nozzle and force the smoke out of it, you will see smoke is diverging. It can converge as well. Water converges though. But if the water converges, its velocity increases. Okay, we'll see it in incompressible fluids. Alright, so we derived it from continuity equation. Right? Let's revise it again. Can we open this? I just opened it. Okay. Now, if density is non-zero, if density is constant, with respect to what? What it means when density is constant? It means density is constant at a given time and at different locations. So there is no gradient of density and there is no time dependence of density, which means divergence of U is 0. So it cannot diverge. Okay.
What is the fleet vector made of again? What does the fleet vector contain?
V is the bulk velocity of the fluid. If water is flowing, the velocity at a given point represents.
So it's just Vx, Vy, Vz. It's just different directions.
Right. Okay. So now we write the Euler equation. So this is a general Euler equation, not for incompressible fluids, right? And we showed that the middle term can be represented as let's take it inside. This we showed in first lecture. Now, because rho is constant, I can write it as gradient of P by rho. Only because it doesn't matter. Okay?
There is a minus sign.
Yeah, I forgot.
So for stationary flows, if this goes to 0, that means the system is not, again, it should always be clear what is the meaning of stationary flows. It does not mean that the fluid is not propagating. It means at a given point, the physical characteristics of the fluid, namely the density, temperature, pressure, velocity, all remain constant over time. Like the river is flowing, you look at the river, you come after 5 minutes, you see the same river, but it is still flowing. That's time dependence. So stationary flows have del V del T 0. In that case, I can write it as gradient. Okay.
Can you repeat it?
Del D, stationary flows. What are stationary flows? What is the meaning of del V del T goes to 0? Or del T goes to 0 in any system? It doesn't mean that nothing is changing with time. Okay? Water is flowing. Okay, imagine an incense stick. Imagine a tap. Okay? My drawing is very bad anyway. Tap, which is a stream of water, is falling down, very smooth, but the water is always falling down. Okay, so velocity is not 0. Physically, the system is dynamic. But do you see the change in the stream over time? No, right? It's falling, it's falling. You do not visualize the change. This is how I see. If you take 2 pictures of it, pictures will be identical. This is how we see it.
The velocity is constant full time.
No. Velocity is increasing because of gravity. Velocity of
For a given space.
at a given space, it is constant or at different times. This is what it means. But physically, you have to realize.
It's like steady state for a given space, not for the whole stream.
For the whole stream,
It changes.
here, here, at every point, there is no change with respect to time.
It's not the velocity of thing flowing through the stream. It's everywhere in the stream, but everywhere locally in the stream. For every fixed point in the stream, and not for a flowing object.
Yes.
At a given point, the system is steady. Velocity and other properties are also same. When we say del T 0, okay, this is what it means. So this gradient is the rate of change in space if a flow is moving, propagating like this, then along a streamline, which not necessarily to be a straight line, the streamline along which the flow moves. If you integrate it over that, you find out so this is Bernoulli's theorem. We derived it before, but now we derive it for incompressible fluids. What's the difference? What's the difference in general Bernoulli principle and the Bernoulli principle of incompressible fluids?
No gravity.
Gravity can be there, we just
You
didn't
can
include
multiply
it.
by rho and get.
Gravity is always there. We
You can assume rho is constant and multiple by it and still get the constant.
okay. So general principle goes like this. Remember enthalpy. Okay. Now enthalpy is entire enthalpy. You can just represent the second term in the enthalpy, just P by rho. It has to be constant for incompressible flows. Once you consider the flows are compressible, you have to include the whole enthalpy term. What is P by rho? For an ideal case, not here.
It's proportionate to temperature.
Temperature. P is rho K. But it's not applicable here. If P equals to P nRT, nKT is not applicable for water. It's for ideal case.
Yeah, because you have different. Yeah, because there's some proportions possible.
Water is not gas. It's not an ideal gas. It's an ideal fuel, but not an ideal gas. Okay. Anything else remaining here? No. Can you read what I'm writing?
Kelvin's theorem, conservation and
Okay, that's important. Conservation of circulation. Now it's an important theorem. Maybe one of the last important things in this segment. Let's define a parameter called gamma.
So for a 2D curve, it's like for a 2D curve.
Whenever I write line integral over a closed surface, it's always a 2D surface.
Yeah.
Okay?
It's like just a path.
Yes. Let's physically visualize this. You take a two-dimensional cross-sectional area anywhere in any orientation, and there's a small line element on that, dl. So what does this integration mean over the closed surface? It means when you have this area, the fluid is flowing continuously in and out as before. Now let's not restrict that the area is constant at particular. It can also change with respect to the fluid.
the area.
Yes. If it diverges, it can diverge. Let's keep it general. Because we will see it is not necessary to keep it fixed with respect to the observer. This is gamma. We call it, okay, we define line integral of velocity as gamma. We'll see why it is defined like that.
So this is defined, gamma is defined for every point in space because you can choose a different point to do the cross section of gamma.
Gamma is not a function of exactly point. Gamma is along, it is a function of point, but it is
Also a function
line
of rotation.
integral of a closed contour.
Okay.
Contour can be big as well, and it represents the properties around that contour. Not precisely point. Okay. Because it's integration. So how you do it? You measure the velocity of the fluid. Let's say the fluid is moving in this direction. This is v, and then this is dl. Similarly, you take v dot dl, dot product of both throughout the this closed surface, and add them all together, and you find gamma. Now, because you are integrating velocity over a closed contour, which is a closed contour has to be, it may not be circle, but it is always like rotating and coming back to it, no matter how we draw it. So this gamma is basically rotation parameter. It shows how velocity rotates in the fluid. Okay? We'll see it is connected to the vorticity or the curve in the flow. So let's try to estimate how it is and what the Kelvin's theorem says. Our aim is to find out what is the time dependence of gamma, which is okay. I'm changing a notation here because it will create a confusion. Let's write this d as delta. Change it because there's a reason why I write it. Okay. Plus,
Is it just for us not to confuse the R and delta?
not confuse between this operator d and this delta.
But it is the same operator.
It is the same operator. But it is important to keep it separate.
It is already confusing with them, so yeah.
To confuse you a little less than what you Okay. Why the second term is coming here? Why the second term is coming?
The change of the region we're talking about.
Dot product.
Yes, but previously we assumed that this DL, because we are assuming this,
It's about
so
the
one could assume that DL does not change with time. But DL can change with time.
Why?
Here we keep it
measure in
general.
different regions over time.
Here we keep it general.
Okay.
The reason why we keep it general.
So it's like the thing you said, the transfer field. The first lecture.
Not necessarily. Even because of the divergence of the fluid, it can change as well. The transfer theorem is when the fluid, the area element changes constantly.
Go to this stuff. Yeah.
Yes. No, in three-dimensional space it can change as well. Here what it means is, because the fluid is moving, it can diverge or converge along so that this line element can change as well. So let's keep it general in there. Now how to define DL? Let's say this is the line element. This is origin. So this is the closed contour and this is line element. DL. Okay? What it means is, if both the ends of the line elements are represented by vectors R1 and R2, then DL simply dr. The change of the position vector with respect to an origin. It's just way of representing. Basically the same thing. So I can write DL as dr. Now, DL, last term, V dot equals V dot L is R, dr over dt. Now what is dr over dt?
Velocity.
Velocity. Okay. This can be written as del. Okay. So last term is simply this. Replacing DL as dr plus now the integral is two different parts.
dr is the line segment.
DL is the line element along this contour. dr is simply R2 minus R1. Two position vectors. The reason why we write it in this form so that we can write dr dt is V. dl dt may not necessarily be. Just way of looking at it. So it is, yes.
Can you explain what is the meaning of gamma? Like, why do you need it?
We are coming at it. Okay.
Oh,
We define it. We look at it what it is. Okay. As I said in the beginning, because gamma is the integral of velocity along the closed contour. The closed contour cannot be linear one dimension. It has to close. So it basically represents the circulation of velocity. But we will come to that. Let's derive it and we will describe it physically, what it means. Why we define this? Okay. It's not random. So it has two terms. Let's separate them. Let's concentrate on the second term. It is a total differential of any quantity over a closed contour. So over any closed contour, total differential of any quantity is always 0. Are you aware of that?
Can we just for like 1 minute just a recap of what we're learning about what is and what is R and what's the principle? I'm sorry if it's
Which principle?
what we're trying to do beyond abstract math. Like what are we arriving at?
We'll see.
Okay.
What we are doing is we define a parameter,
Yeah.
gamma, which is
Circulation in a
the
region.
circulation. What we'll see. So it's basically what we defined is integral of velocity over closed contour, line integral.
Yeah.
And then we are trying to find out how it changes with time.
And we're assuming the
Why we are finding it out, we'll see it shortly. We are assuming
and the region can change.
region can change with the stream.
And what was the thing with DL and DR?
Here and here same thing. It's just the position, two
Yeah.
position vectors dr. So dl dt is basically dr dt. Shows velocity of the field. This is the way we define it, and we wrote it in this form.
Okay.
Now concentrate on the second term. It's a total differential. Integration of total differential. And I said it is 0. Are you aware of that? Why it is 0? It means any quantity, if you take total integral over line element, it is always 0. What?
Yeah. Yes.
Because this is simply right. Integrate it, the limit x to x1. Now what is x2 and x1 for closed contour?
The same point, 0.
It's starting from here, coming to the same point. Okay. So basically these two are same. So it has to be 0. Okay. And it's true for any quantity, including v square.
This goes,
What?
goes
This goes
always 0.
always. This term is 0. Here. Because it is. Yeah.
So why didn't we say that from the beginning?
Why? If you assume that it is, if you assume that the line element does not change with time, you are putting an extra condition on the system. The line element has to be fixed. We showed that even if you assume the line element is not fixed, the theorem is that we are going to derive is still general. You got the point?
Yes. Even if we don't think that from the at this condition, it's always 0, no matter what.
If you add the condition, the theorem that we are going to derive, you will understand that it is derived for a specific condition, that the line element is constant over time. We assume that even if it is not constant, the theorem still holds. So it is important not to assume it in the beginning. You got the point?
Yeah.
And one more question. You said in the offset on the left, you said like that on the thing on the left you didn't cipher. What you're more left. This you said that dr over dt equals v. So we're talking about the motion specifically, like we're talking about not just any general change of the curve, but the change that moves with the particles.
This is why we assume that this line element is defined by the vector of the velocity.
Yeah.
You have to keep it general, it's important. Okay. Alright, so this term goes to 0. So we obtain that. Real algebra. Now from Euler's equation, what is dv dt? This is from Euler equation. What is it equal to? Euler's
We
equation.
have from Euler's equation. What is it? V minus V. You remember it?
I don't remember it. Tell me.
Minus V dot grad.
No. V dot grad is in this. It is total differential.
Yeah.
Okay, hold on.
I said del dot
This is del V del t plus V dot grad.
minus
V. Right?
and then V
What is the right hand side?
to minus P over rho. Minus del P over
Minus grad P over rho. Minus grad P over rho in general.
plus
And for isotropic flows,
A. Then
these things should be in mind always. So they're very basic. It's grad W.
just equals W.
Enthalpy is gradient. Okay. Now this is gradient. If you take a closed contour, the gradient of W along with the closed contour will always be keep 0. It's another theorem. The gradient of a function, if you take its integral over the closed contour, it turns out to be 0. Because the gradient shows the perpendicular of the surface. So this goes to 0. So what we found out that the rate of change of this gamma, which is 0.
Why the 0?
What?
Why the gradient of the enthalpy 0?
When you take the gradient of any function, it shows the perpendicular surface.
Okay.
So you can it can be an arbitrary surface, but when you add all of them together, they finally turn out to be 0. So along the circle, it's easy to measure, but it's true for any closed surface. So what it shows? This equation shows that gamma equals constant. Or gamma is independent of time. So the quantity that we define as a circulation, it does not change with time. In what? Which flows?
You assume here the enthalpy.
Isentropic.
Ideal flows and isentropic flows. We can convert this into curl. So this curl of V, its surface area integral is always constant. What it means? This area cannot be 0, which means that the circulation, this curl of V, it remains conserved along the streamline and different times. So it's called Kelvin's theorem, where it shows that the circulation in an ideal fluid, isentropic fluid, remains conserved. It's conservation of circulation. This del cross V is also called vorticity. Now this can change. The vorticity does not remain conserved if you have dissipation. Give me an example of dissipation, we'll see it.
Stir a cup of coffee and it stops. When you stir a cup of coffee and it stops.
I didn't hear it.
Stirring a cup of coffee and then it slowly stops.
What will happen if you stir a cup of coffee, which is the coffee is ideal?
Okay, so you give it circulation. Because if you look at a specific moment, you look at the velocities along the curve, it's positive. Then what?
When you induce a circulation,
It's creating a vortex.
vortex. This is vorticity. You can create a vortex even in an ideal fluid, but that vortex remains conserved. Which means if you induce energy in a cup, it will keep on rotating. It will not dissipate, but it doesn't happen. It dissipates itself, and
That's dissipation.
that's dissipation. We assume no dissipation. But let's look at another example, simpler one, so that we can have a physical picture of this. Assume a surface on which a fluid is flowing. This is a solid surface. So generally what happens when fluid flows over a solid surface?
It's like friction.
What is curl? Curl means if you put a pinwheel in a river, if the pinwheel starts rotating, the curl of the fluid is non-zero at the point. If you put pinwheel here, it will not rotate, right? It will flow. But if there is a solid surface in your daily picture, what happens? Now this fluid is viscous. It's not ideal fluid. So this lowermost surface attached to the fluid. It doesn't move. When the water flows on rod, the lowermost surface sticks to the rod, and the upper surfaces keep on moving, and there is a gradient. You might have studied this viscosity in the classes. These upper layers are moving faster. So there is a difference in the speeds as you go up. It automatically induces a kind of curl here. Okay. So the moment you put a dissipation, the curl can be generated. If there is no dissipation, it cannot be generated. You can generate from outside, but the moment you leave the system, which is asymptotic, you do not induce any energy. The circulation remains conserved over time.
But in this situation, circulation increases. Because, I don't know, when you say dissipation, makes me think things are only decreasing.
No, it can induce circulation as well. When the fluid is turbulent, it has random circulation at different places.
But there must be something that is decreasing, energy or
Some
there must be a quantity that is decreasing, that is being lost to dissipation. Is that energy?
Yes.
So in this
Generally-
situation,
Generally it produces heat. Because the friction between the surfaces,
yeah,
it produces heat and energy dissipated.
and heat takes energy away from the velocity. So
Yes, ultimately it will stop.
okay.
You stir
Yeah.
water in a bucket and leave. What do you observe?
Stops.
It stops ultimately because it is dissipated energy. Alright, anything remaining here? Okay. What time is it? I didn't bring my watch.
4:55.
Not far away. But this del cross V is not zero. It is non-zero but remains constant. Now we'll discuss a specific situation where del cross V is zero in a fluid. There is no curve. If del cross V equals zero, the fluid is called irrotational. Okay, and there's a name for these flows which is called potential flow. If del cross V is yes,
But if the curve of the velocity is zero, it's not really a property of the fluid. It's more a property of where it flows. So calling it irrotational is a bit weird.
irrotational means there is no rotation in the. It's mathematical term. It simply means the curl is zero. This is what we
There is no fluid where there's no way to rotate it, right?
It is not rotating. This is an imposed condition. We'll look at a couple of examples. So vorticity is zero. But these flows are also called potential flows. Why?
Because you can define, like, because it's way easier to describe a vector field that you can describe with potential.
Right.
It reduces your degrees of freedom like a lot.
You have heard of conservative force fields.
Yeah.
Gravity is a conservative force. What it means?
Potential.
Electric field is conservative. So
It
in
means
electrostatics, electric field is conservative. In electrodynamics, may not be. If del cross E is zero, so again, electric fields are irrotational by definition. So you can define E as minus grade phi. Because when I take the curl of it, this is anyway zero. So any quantity whose curl is zero, the quantity can be defined as a potential. In the same way, we can define this velocity. V can be defined as minus grade phi. And phi is velocity potential. Now if we write Bernoulli Euler's equation for potential flows, we'll have a couple of examples of potential flows. Okay, how it turns out in physical systems. This is Euler equation for asymptotic flows, and we showed that the second term can be written as if the fluid is stationary. Again, del V del T goes to 0. It's the same Bernoulli's theorem, but there's an important difference here. The difference is that for potential flows, if there's a flow with different streamlines, the Bernoulli constant can be different for different streamlines. But because the vorticity is 0, for all the streamlines, this parameter is strictly constant for potential flows. That's the important distinction between potential flows and normal flows. Just how you look at it.
So these are like streamlines, I guess. No.
Streamlines. Different streamlines may have different Bernoulli constants in general flows, but the moment you impose that del cross V equals 0, there is no vorticity. The Bernoulli parameter or the Bernoulli constant has to be same for all the streamlines.
So if you have a potential which is like a slope that goes down in the direction of the flow, can you also have a field
That's a gravitational potential.
perpendicular?
That's gravitational. You mean gravitational potential?
I mean the velocity potential. You define the stream. If you have a velocity potential, which is just like a function, is like a function in free space, you can define the velocity based on that, like the gradient of that. Now you have here something that is constant for every single streamline. Can you have a function that is perpendicular to that? That is like different z values of that. I think about it.
You can define phi in any manner in three
Like a
dimensions.
streamline potential, like something that is perpendicular to the velocity potential and is for.
So always perpendicular. When you define V is grade phi, this grade phi is always perpendicular to this. The gradient by definition is perpendicular surface to the field. If you define an arbitrary function like arbitrary surface,
I didn't explain myself well, so never mind. Continue.
any arbitrary surface, phi, defined in three-dimensional space,
Yeah.
the gradient of which is always perpendicular.
Okay.
This is how it is defined.
That's good.
Okay. So we take an example of potential flow. We take one example, then we'll take a break. Okay. consider volume with fluid filled inside. That's a gas or water or anything. We go with our assumption that the fluid is ideal and non-dissipative, of course, ideal, and the asymptotic as well. Attach a mass with that. Attach with a spring. If I displace this mass a little bit and leave it, it will start oscillating. Right? Small oscillations. Small oscillations means oscillation amplitude A is much smaller than the length scale of the system. It's a small oscillation. Now when this will oscillate, what will happen? What will happen to the fluid?
Bounce with the...
Yes. Like when I'm talking, when I'm speaking, it's a small oscillation of my pharynx. It's affecting the air. It's affecting the air. Then what is transmitted to basically the cell. The moment it, yes.
We're forcing the velocity of the air on the boundary to be equal to the velocity of the thing. Right?
So when this body oscillates, it will affect the velocity of the fluid nearby. We want to see that how this motion of the fluid, because of this small oscillation, is a potential flow. Just as an example.
How does this change with if the fluid is condensed or not? If the fluid is condensed or not, the oscillation will be even less strong, but how it will affect the fluid?
If the fluid is very dense,
Yeah.
and spring constant is let's say the spring is constant. Spring constant is constant. Keep it fixed. If the fluid is pretty tenuous or density is very small, it will oscillate. It will oscillate higher. If it is very dense, suppose it's honey, it will not oscillate at all. That's the question.
So the fluid itself will put forces on the tube or the nuts.
It's resistance. Fluid works as a resistance. This is what we are studying. When you give the small oscillation to the system, fluid oscillates along with that. Yes, oscillatory motion of the fluid, whether it is a potential flow or not, we just want to have an idea. Euler's equation. Now, this A is much smaller than air, so it has to be small oscillations. And there are two velocities here. Velocity of the fluid, which is bouncing back and forth because of the motion of the oscillator, and the velocity of the oscillator. The velocity of the fluid is definitely V. The velocity of the oscillator, let's call it U. Okay? Now they have to be the same.
Boundary.
Yeah. At the boundary of the oscillator in the nearby region, these should match together. So this V dot grad V typically like this.
Why is it?
Because this V is same as U, and the gradient of the V is of the order of okay. So this is amplitude of the oscillation. The velocity can change up to the amplitude. So the gradient, basically the order of magnitude estimates are similar to like this. Okay. So this term is roughly similar to okay. How about this? If the frequency of the oscillator is, let's say, omega, we call this omega. Okay. Then this del V del T has similar order as omega u. Omega is per second. How the velocity changes of the fluid? It changes with the frequency of the oscillator.
That's fair.
And this omega can be represented as y. U is the speed of the oscillator, A is the amplitude. So combining these two, there's an error here, this is not A. Why? This velocity's gradient changes over the length scale of this system. The oscillator is oscillating only with the distance A. So this term is u square by I, while the speed or grade V is not u square by A, it's u square by L. Why? Because the fluid is oscillating throughout the walls of the chamber. Why? You get the difference? I made a mistake. It is not A, it is L. When you write V dot grade V, the velocity of the fluid, up to what scale the velocity of the fluid changes? The entire system. Up to what scale the velocity of this, the frequency depends on only U. So this term is u square by A, this is u square by L. So it was wrong, it is u square by L. Okay.
Is this estimate of velocity squared over the length scale, is this just a general fact of oscillators, or did you get it from somewhere?
Say it again. Velocity changes despite.
Where did we get u squared over A or over L from? Where did we get either of them? You said omega equals u over A, that makes sense. So then V times omega.
Omega is 1 by T. Omega is 1 by T.
Yeah. So yeah, okay.
Yes, U is the oscillation, A is the amplitude. We are just trying to see the order of magnitude estimate of the different terms. So which term is bigger out of these two?
That one is for the A.
The assumption is that A is much smaller than L. So this term is much bigger than this. For the small oscillations, all the assumptions we have. That means still goes to 0. Okay? So we have, now we write the full term again. Del V del T equals minus grade U. Take the curl both the sides. Minus curl. This is 0. Curl grade U is 0. Left hand side is V, not U. No. What it means? Is it a potential flow?
No.
No?
That's going to be 0.
Yeah. So it is Kelvin's theorem, but what is the direction of V? It is oscillating fluid. So when you take the time average,
So it's this one.
this side, when you take the average,
It's
it turns out to be 0. Okay. So for this particular setup, this constant has to be 0. Why? Because in the oscillator system, the total time average of velocity is 0. Which means that when in ideal case, when I'm speaking, my pharynx is oscillating against the air. If it's normal system, this motion of the gas is curl free. It cannot induce any curl. Is it always true? Like we have a ring or bell here. Okay? It's difficult to visualize the pharynx. Visualize something which is oscillating here, and the air is oscillating like that. Is it necessary that its curl has to be 0?
Well, it's changing with time. So,
Time average. Time average then must be equal 0. This constant is 0. This constant is 0.
well, shouldn't the long-term velocity, the average velocity be 0 though? Otherwise, a vibration would give you like more material
But if you observe this air,
on average.
but if you observe the air, there will be always be many curls in the burst.
Why is the constant have to be 0?
Its constant is not 0. The del cross V is 0. It has to be constant. Okay. Because your time average 0 is a constant, not to be confused with. Because when you take the time average in the oscillating system, the curl of the velocity turns out to be 0. So it's a potential flow. But if you see in reality, you will not find it to be 0. Why?
Because in reality, nothing is ideal.
Not ideal.
It's not a closed
Yeah,
system.
energy dissipation.
You can keep it a closed system.
Even in closed
Your answer is right, but let's look at it from physical point of view. How the curl is created. The oscillator is oscillating here.
Oh, it's like what you said with the surface. If you have like the boundary of the belt and you have a little pinwheel, then on the side of the boundary, then you won't have any air. Like you have movement, so it's like it forces the curl. It's like the curl forces movement.
If it is ideal fluid, then
Yeah.
it still forces.
Yeah, sure.
Right, you're right, but what he wants to say is that if it's ideal fluid, the force is like there is no interaction, no dissipative interaction between the solid surface and the gas. The moment the fluid is non-ideal, there's always dissipation. The dissipation may cause curls. In reality, you will always observe. So, practically, it is not possible to have an ideal fluid because a flow cannot pass through the solid surface. If you have a fluid like that, if you put a ball in the fluid, it will dive. It will have two streams, right? The two streams are possible only if the fluid interacts with the surface of the solid. The interaction is not possible if the fluid is ideal. So ideal fluid is just an idealistic assumption. Theoretically, even it cannot exist. Now, there is an example which is very close to ideal fluid. Frictionless. Superfluid. However, liquid helium, it almost does not have interaction. But the problem with liquid helium is it is not a Newtonian fluid. So it's kind of part of it. So it doesn't even align with this equation. Alright. Show me time. What should I take
It's
my time?
5 minutes closer.
5 and
60 minutes.
5:16. So let's take a break, small break. So here we are done with the ideal fluids, whatever we had to cover in the course. We will go through everything and I will put up the next assignment tomorrow. Everybody submitted the assignments?
how to say?
We'll talk to you after the lecture.
Okay.
We got it.
Okay. Alright. So I give next assignment, which is the 2 assignments for the first task, which is ideal fluids. So after after a little bit, no? But I will give tomorrow.
Okay.
There will be 2 assignments for this section.
2 assignments tomorrow.
Second assignment.
Or second.
And then after the break, we will go into dissipative fluids. We will look into turbulence. We will become more realistic. Now we are in fiction. Any questions by now? Okay. We have finished the discussion of ideal fluids. Any confusions? Within the break, you might have thought of something. Okay. Good. Now we'll try to formulate how the equations of some people are coming. Anyway, yeah. So we formulate the same equations for real fluids. When I say real fluids, means of course not ideal, but we can see them in 2 parts. One is viscous fluids, other one fluids with turbulence. Turbulence and viscosity are different things. You understand that what is viscosity, what is turbulence?
One is condensed and one is
What do you condense? What is viscosity? It should be in the schools, right?
Viscosity is like a column of fluid is moving, column of fluid next to it is stationary. They will sort of be dragging each other. Like, sort of like
friction.
Friction within the layers of fluid. That's viscosity. And turbulence?
But you said you can have circulation in ideal fluids too. So what's turbulence if it's not circulation?
No. Okay. So there's a distinction. We will go to both of them pass by pass. But first, in next few lectures, we will be dealing with viscous fluids. Okay? Viscous fluids means honey, everything is viscous. Water is also viscous. Viscosity is less. Okay? Viscous fluids means when the fluid flows, the different layers of the fluid interact with each other. They drag each other. It's basically molecules are interacting with each other. If you imagine a fluid, imagine the particles in fluid, different layers. In ideal fluids, what we assume is each of the infinitesimally small layer is not interacting with another layer in any way. But now go microscopic, at microscopic picture, and you see particles randomly moving. The particles are always going from one layer to another, right? So when they go from one layer to another, that means that the assumption of non-interacting layers is technically unfit. Okay? Particles always interact with each other, so layers always interact with each other. Now if you induce a circulation, as the question came, let's say in a cup, water just starts rotating. But it's very possible, we are in the viscous fluids. Okay. So if the fluid is rotating like that, it doesn't mean it is turbulent. Different layers are, it may not even be viscous. It just means that the rotating layers, they have velocity, there is a curl there. But if the rotating layers do not interact with each other, even with the curl, the fluid can be ideal. A rotating fluid doesn't mean it is turbulent. It just means it has non-zero curl, it has a rotation. It can even be ideal, where the rotating layers do not interact with each other, do not drag them behind. Okay, so these are completely different things. You should have a clear picture in your mind. When you rotate the fluid in the cup, it slows down with time, even if it is not turbulent, and it stops it there. Why? Because of, if it is not turbulent, it is because of viscosity. So now we look into it. But the better picture is of flowing water on a surface. So when we try to physically, not mathematically, when we formulate this, how the Euler equation should look like. Euler equation we derived. It's the rate of change of velocity or the momentum transfer in a fluid. How it looks, we saw it very carefully. What will happen if there is a viscosity? We try to physically imagine it first.
Then you have sort of momentum diffusion.
Momentum diffusion is there in general Euler equation as well. Momentum always diffuses.
Why was it? Oh, because. Okay.
So in ideal fluid, we saw that when the fluid passes through any surface like that, the momentum flux of the momentum phi I k. It's always in the direction of the bulk velocity of the fluid. It's vector. But if there are two layers, this adjacent layer, if this layer is dragging it down, there is a momentum transfer from one layer to another. That's the difference. Now we are just physically picturizing. We will go to mathematics. What it means is the momentum flux may not just be parallel to velocity. It transfers its momentum in any direction. It can, okay? Perpendicular to it as well. So it means there is a momentum transfer within the fluid in a viscous fluid.
The momentum transfers in like all directions.
Only
All the, I mean, you just said that momentum transfers from Moksh plane to every direction.
okay. Let's make it clear. Come to classical mechanics. What is momentum transfer? If I change the momentum of any, if some car is moving like that, and I try to stop it, I'm reducing its momentum. If I push it, I'm giving it momentum. So momentum transfer from one point to one system to another system takes place the transfer of momentum. In an inviscid fluid without viscosity, the momentum is conserved, but locally, the moment you talk about viscosity, when we say that one layer is dragging another layer down, so assume that two layers are two different systems. One system is moving in an invasive way. This layer is dragging it. What is drag?
It's
Slows down.
Like friction.
Slows down. What is slowing down? Momentum is decreasing. But where the momentum is going?
into the other system.
Transferring from this layer to another. So now there's shear transfer of momentum. Okay? That's the most important. That's the only point which is required to for you to have a picture of viscous fluids.
Shear transfer of momentum in that direction. In the direction of the
Maybe perpendicular, may not be perpendicular. Depends. Maybe even complex. But it transfers the momentum between layers. So it's shear transfer of momentum. And a typical example of this is flowing water on the rod. Flowing water on the rod, if it is ideal fluid, what will happen? If the rod is, let's say, flat, it will keep on flowing indefinitely. But the moment it is viscous, the surface is anyway stopping the lowermost layer, but the first layer is slowing down the upper layer because of the interaction. So you will see that the momentum, there is a gradient of momentum as you go up in different elements of the fluid. It is coming because of viscosity, and what it means is there is a transfer of momentum across the different layers, with different streamlines. Okay. So we start from Euler equation that we wrote in tensorial form. Okay, familiar with that? What is pi IP here?
Describes the transfer.
Momentum flux. What is momentum flux?
It describes the change of
It is
PUI in the direction x.
rho vi vk, there I get p. P is isotropic. We spend time in understanding its physical meaning. Okay. So until now, we assume that this momentum flux does not transfer the momentum between the layers of the fluid. It's conserved. When you formulate the viscosity of viscous fluids, which we just tried to understand physically, what? Okay. So we saw that the momentum is transferred between various layers. To mathematically formulate that, this momentum flux has to be between the different layers. So how it should look like? It should look like the momentum flux.
Is not parallel to the velocity.
It is always parallel to the velocity, but then it should have additional components
Yeah, component.
in different velocities. So basically, it has velocity gradients across different layers. So it should be composed of some terms with like that. Ith component of velocity changing with kth component of gradient. Along as well, sides as well. So it should be composed of some different kinds of velocities. So for a viscous fluid, now we have to introduce some terms so that this momentum flux incorporates the velocity shear. Sigma I. Now we'll find out what is the physical nature of sigma I. Call it sigma prime I. Call it prime. Now these two terms all together, we'll shortly see what is the nature of sigma prime. These two terms. This is viscous stress tensor. It is tensor, it is two indices. So the additional term that we added, sigma I k prime, it's called viscous stress tensor. It is applicable when the fluid is viscous and there is an interaction between various layers. This is how it is represented. Here, theta and xi. Coefficients of viscosity. So this tensor is shown in terms of various terms, which all include the derivative of velocities with respect to different coordinates. Del V and del x k represent 3I and 3k.
So it does include when I equals k.
Yes, it does include. Okay. Viscosity means the momentum transfer can be anywhere.
Even on the
even on along that. But the difference is, if viscous tensor is 0, the momentum transfer still takes place along the motion of the fluid.
on here.
But consider you are imaging you are co-moving with the fluid. Okay? The fluid is flowing like that, and you imagine a small volume element which is propagating along with the fluid. So in locally, if an observer is moving with the fluid, it does not see that the fluid is moving. Okay?
See
Now, a small point.
Yeah.
So it sees that in its observer, in its frame, it sees the observer that the fluid is constant.
But you can't see if it changes direction.
Changes the direction, but its co-moving observer is changing along with that as well. Assume that it is moving in straight lines, so not changing directions for simplicity. For co-moving observer sees a volume element which is fixed, very small. Now, in this frame, where can the momentum transfer take place? Nowhere. In the co-moving frame, momentum is fixed in this volume, unless it is expanding. Let's assume it is not expanding as well. If it is expanding, it will see momentum is transferred. That's a different point. The moment it has viscosity, then it will see that not only the layers which are perpendicular to the flow, even in the nearby layers, the momentum transfer takes place because particles are interacting everywhere. So this term shows that how the momentum transfer taking place in shear layers. When you see this term, when V and K have the same coordinates, it can also take place, transfer takes place in the same direction. However, if the fluid is ideal, this is also not zero in that case. So it cannot take the transfer cannot take place in any of the directions.
Why is it zero if the fluid is ideal?
The whole term is zero. This is zero. This sigma ik is zero. This viscous transfer not only takes place in adjacent layers but takes place everywhere. The first term here is, so there are two viscosities here, eta and xi. This eta is shear viscosity, the typical viscosity that you are aware of. When you look at a fluid which is flowing on a surface, the layers are changing speeds, that is a shear viscosity. If you have done the chemistry's experiment in, you do experiments, right?
Yeah.
You have chemistry?
What?
Chemistry? No. Physical chemistry? No.
It's a course in third year.
So I'm not sure how the experiments are performed here, but in our graduation we used to use Stokes' law and find the viscosity of the fluid. So viscosity.
Oh, we did that.
We did.
That's in the general lab in the first year.
Yeah, we
So
did.
I saw him at
Yeah.
What experiment is it?
ball falling in a vat of viscous glitter. Measure
Okay. You put a small ball and then its speed increases and its speed becomes constant.
Yes. Yeah.
Yeah.
Okay. So what viscosity you measured there?
That's a year ago.
I think we measured eta. Remember that?
Huh?
I remember the viscosity being eta. Like that.
Eta.
Yeah. Is that what you're talking about?
Yeah. But here the fluid is not. But there's an interesting question here. In that tube, the fluid is not moving at all.
Right.
Why this was what is here?
Because the ball is moving.
Ball is moving.
In the
We
moving
can say the
frame,
ball
it
is
stays with the
static
ball.
and the flow is.
Yeah.
You cannot. It's dangerous. Okay?
Okay.
I told you that so when a solid object moves, it has a physical problem. When a solid object moves, it's an inertial flare. But when liquid moves, it's a non-inertial flare. So it's still similar, but what's going on here is when the fluid flows, momentum can transfer from one point to another. But when the fluid is steady, we made this, I did it 10 years ago, we did it 15, 20 years ago. The same experiment. We had to break the tube lights, you know, bulbs.
Oh, okay. Like this.
In India, we have these white bulbs, we call it tube light.
Okay.
They have glass fluorescent lamps.
Oh, yeah.
So in our lab, when we designed this experiment, we took out the tube light, opened its one portion, put the glycerin inside it, clamped it, and then brought these marbles, steel marbles.
Yeah.
And we did the experiment with that. When you design the experiment like that, you never forget. If you do experiment like this, you know, you forget that you did it few years ago. I did not forget I did it 15, 20 years
Only a year ago, not you.
ago. Alright. So, why viscosity is coming here? It's good that we saw the example. Now, we talked about that when a fluid flows, it transfers momentum in adjacent layers. We're basically talking about the first term. We'll talk about that in the second term later on. But when the fluid is not flowing, these all terms should be zero in that case, right?
Yeah.
Then what do you measure?
That's a good point. Well,
I did not think about this point before asking the question.
Can you repeat the question?
The question is, here I talked about when a fluid flows,
Yeah.
it can transfer its momentum from one layer to another because of viscosity. But in the experiment we are talking about, you have a glass filled with, let's say, water or glycerin. You put a ball, drop a ball inside. How do you calculate the viscosity when the fluid is not even flowing? When the fluid is not flowing, ideally all these should be 0. There is no V. V is 0. V is 0, then all terms are 0. Then how do you calculate viscosity? It's not difficult question. Think about it.
Then what's the answer?
Okay. The ball is flowing, as he said, which is fine. Thing is, when the ball is flowing, suppose the ball is like that. So the ball drags the nearest layer of the fluid is attached with that. So when the nearest layer is attached, so whole fluid is static, but the one layer attached with the ball is attached. It's not moving at all. It's going with the fluid, going with the ball.
It's like a boundary condition. You know the velocity at the edge has to be equal to the velocity of the ball, because otherwise fluid will be going into the ball or outside of it.
No. In ideal fluid still follows that boundary. Ideal fluid doesn't go inside the ball, but it doesn't do what you're saying. Okay? I mean, what you mean is V dot N is 0. It cannot penetrate the ball, but that's not negative.
Okay.
It's just the friction on the surface. So the boundary condition here is at the surface of the ball, whatever the fluid which is attached to the surface, it should move with exactly the speed of the ball.
Oh.
In the ball's frame, that layer is not moving at all.
It's not just V dot N is 0, it's just V equals U.
Parallel.
Oh.
The parallel V between the two layers is 0. So what we can assume is this kind of ball. Okay? Let's rectangular ball. So, and imagine there are two layers. The ball drags this layer along with it. And this layer is steady. But there is an interaction between these two layers. So what will happen? As the ball passes, this layer, the momentum is transferred.
It will oscillate. It will do, the ball will oscillate.
Let's say the ball doesn't oscillate at all. It doesn't. Keep it simple. The ball is just falling down.
The layer closest to it has to be equal to it in velocity.
The closest layer has to have the velocity
Equal.
equal to the velocity of the ball.
Okay.
Let's say it's U. And this is also U. Then, now it's a viscous fluid.
Now it's a viscous fluid, so
So
the layers to the left will also acquire velocity because there's interference between them.
the momentum is transferred from where to where? Momentum transferred from where to where? Which direction the momentum is transferring?
Upwards. So,
No.
why?
Upwards.
Perpendicular to the surface of the ball.
Upwards.
So in at t equals 0, the momentum of this layer was 0. It's not moving. Now it is starting moving. Yeah, it is taking momentum from here. This layer has taken momentum from the ball, but this is because of the interaction with the solid surface. Now there is an interaction between different layers. So this layer, this moving layer drags this layer, so it starts moving, this also starts moving. And then there is a gradient that you start getting this dV here. Okay, so V does not remain constant. Even if bulk velocity of the fluid is 0, the layers associated with the ball, they are dragged, and adjacent layers are dragged by the other layers. So then you see the gradient and the dissipation takes place. So this first term, which shows the gradient across different layers, this is called shear viscous terms, shear stress. Shear stress. Okay. So when you calculated viscosity, you calculated this. The second term is bulk stress. bulk stress means, okay, what is in the bulk stress? It is del VL del XL. What is del VL del XL?
Just gradient velocity. Right? No. It's V dot grad V.
No. Where is V? Don't throw the terms. Where is V here? It's just one.
VM.
No, you have to
But different times.
just think of it. What is del VL over del XL?
The change in its acceleration.
It's divergence.
Okay. Okay, yeah.
Divergence. Del Vx del X, del Vy del Y, del Vz del Z.
And we're summing over L, so it's actually divergent.
Divergence is divergence.
Yeah.
So volume, if the last term is divergence of velocity, what it means? It has very beautiful physical insight.
Divergence of velocity, we talked about it when we had density, when we had the incompressible fluid.
Incompressible fluids, for incompressible fluids, that term is zero.
Yeah.
That means when you calculate the viscosity of water and glycerin, that term, that psi is always zero.
Okay. So this term controls change in
Changing?
density? Change in density?
Yes, but precisely change in volume.
What?
Change in volume.
Okay.
But if it's an ideal fluid, ideal gas, volume can change there as well. So change of volume doesn't necessarily mean there is a viscosity. Okay. So far we have been studying ideal fluids which were expanding, there was density which was changing. But there is a difference here. The difference is psi, which is bulk viscosity. Let's call it bulk viscosity. So now imagine expanding fluid element. When the fluid element is expanding in an ideal fluid, the dissipation does not take place because of the viscosity of different layers which are expanding together. If the fluid is viscous, not necessarily that the dissipation has to be only in the layers, it can be everywhere. When it is expanding, expansion also transfers momentum, but that transfers due to divergence. So this is why you do not have cross terms here. So the cross terms show shear viscosity, and this shows volumetric expansion. It's clear? So even if an ideal fluid expands, psi is zero. When I say sigma is zero, what I mean is eta is zero and psi is zero. Okay? These terms are anyway not zero. These terms are not never, they are always there. Velocity can change, but they do not transfer momentum until you have eta and psi. Eta means the transfer of momentum between shear layers, and psi means transfer of momentum between different layers where the fluid is changing its volume. Alright? In water, glycerin, whatever experiments you did, you measure only eta. Psi is zero for that because it is divergence. Even in eta, this term will be zero.
So for the ball that is falling, the eta velocity, the eta viscosity, shear stress doesn't matter because there's no, it's just that one.
But if the ball is falling in air,
Okay.
then this term will always be there. Because
All right.
these nearby layers can expand as well. Exactly what will happen, I am not aware, but yeah, the volume can change near yes.
Why do we have a factor of 2/3 in the equation?
It is just a way of representing all the terms. If you write, we'll expand it in next lecture, and then we'll put it in the Euler equation and show you exactly how it turns out.
Okay.
But the purpose here is just to understand it physically. I was not supposed to start this today, I was just finishing the inviscid flows, but because we finished faster, so I thought we can have physical picture of that. We'll put it in the equations, we'll expand it, we'll try to see how it exactly represents.
Okay.
So it should be clear here.
Can't we enter it into the zeta? It's like we have both the delta with the same derivation. Can't we just put the 2/3 with the zeta?
No, because okay, it's a good question. You cannot do that. The reason is you can do it, but then in that case you will have cross term. Eta is here, right?
Okay.
You can put it. Then there will be eta zeta. You can take it here in the table. Why
set zeta otherwise?
Why the two
Why is
terms
it
are
like
set?
that?
It is like that because it characterizes two different types of viscosities in the fluid. One is the shear viscosity
Okay.
between shear layers. Other one because of the
So
bulk
we just need the component here with the eta to cancel things in this part.
Yes, this is why it is
expression.
separate. Yeah.
Okay.
The common terms are just when these are the terms Vi, Vk. This will also have del Vi, del. Right? Del Vi, del Xi.
Yeah, of course.
Then you take these terms, they just cancel out, only shear terms remain. We'll do it in
But it doesn't cancel out exactly because you have 2 here and there's only minus 2/3.
It will. We'll expand it, we will check it and we'll put it. Okay? The equation will derive the Euler equation, but the purpose is this.
I understand. I just forgot the Zohar summation.
The summation, there are many terms.
Okay, I understand.
I could put the whole combinations, subtract the common terms, but we'll
I
talk about
understand
it.
now.
We'll talk about
It's
it.
okay.
Yeah.
Thanks.
But still, when you write these in separate form, it's because there's two physical meanings of eta and xi. Okay. I think we stop here. Yeah. Very good. Yeah.
What does it mean physically if I set sigma to 0 and then I say that minus the shear viscosity term equals to the bulk viscosity? Like, what does it mean physically?
What does it mean? What is sigma is 0?
Yeah, sigma is 0.
When sigma is 0, it means eta is 0, xi is 0.
Can I say that minus this term equals this term?
No.
No?
Okay. This is a very important point. Your question is, I think, can there be a combination of eta and xi that the whole, even if eta and xi are not 0, but the whole term turns out to be 0?
Yeah.
It doesn't happen. The reason is eta and xi both are positive. Okay? The moment both are positive, this is a positive term, this is positive. This is why, in order sigma to be 0, both have to be 0. In incompressible fluids, xi is 0, but eta is non-zero. But if eta is 0, even in compressible fluids, if it is non-viscous, both have to be strictly 0. So basically eta is everywhere. Xi is specifically for fluids that can expand and contract. Okay. Clear up to now? So we'll derive the equations of motion in the next lecture. Okay. Antonyms. Yeah, we are turned to that. Number is people. Yes. Was that 5 days period enough for the assignment?
5 days?
Previously, the first assignment I gave 5 days. That was a pretty small, cute assignment. This week? Then cut-off date. The cut-off date is.
Would it be possible to extend that?
That's what I'm asking. You can take your time, but how long you want? You cannot want 1 month.
We talked about it before. We said a week and a half.
A week and a half, 2 weeks
That'd be fair.
would be great.
Okay, maybe I can keep it 10 days.
10 days is very good.
Wait.
Give us a bit of time if you have something.
First, in the first assignment, it was very simple one. Nothing much, just physical examples, etc.
Yeah,
Correct.
the first time
It was a lot of it.
it took a lot of time to write.
I understand it's a problem, okay? But you should understand it's a problem for you to write, even if you want to type. It's a problem for me to understand Ganesha. So it's your life is hard, my life is hard.
So why not? Let's just type.
No.
Why?
You will not type.
Why would
It's a
not?
human nature. If I want to, I will waste my time. You know what will happen? Okay, I don't know. If I give an assignment, some people are very clear. They just put the assignment, take a screenshot. Even 6 years, 7 years old child can do that. Put it on ChatGPT, will solve, find the answer. It will put a LaTeX and will produce PDF. You attach. You didn't even need to look at the question. However, I'm not against artificial intelligence.
You can still just enter it into the computer and copy it manually.
So when you copy it, at least you learn something.
Yeah.
You copy it,
I agree.
copy from the book, copy from the whatever. You write it and learn it. I know it's not convenient. I understand your problem, but it's not convenient for me either. I tried to open some of the assignments and it was. I didn't check it yet, but it was not like.
יש לך עדיין 9 או
How fast are we? 6:30? You finished writing? Next. 10 minutes.
Can I ask you something about it?
Yes, yes.
It's about the upper and lower messes. I know it's not in the course. It's not part of the course, but
What are you covering?
yeah, you have one upper and one lower in this, right?